What's up, AP Psychos? So we are on to our fourth video, I believe. Yeah, fourth video for sensation and perception. We're going to wrap up the sensation part of this unit with our other senses, specifically touch, taste, and smell. So let's get into it. Our first one we're going to talk about is the skin and body or somatic senses. This is our sense of touch. And our sense of touch has four distinct skin senses within it: pressure, warmth, cold, and pain. So we have these receptors that kind of help us identify these things through our sense of touch. These skin senses, of those things, only pressure has identifiable receptors. All other skin sensations are variations of pressure, such as warmth, cold, and pain. And you can see the different receptors and the way that they look. These neurons are a little bit different in the way that they're structured when you're taking in pressure versus different vibrations. Cold, warmth, and pain all look like this, right? So pressure is a big one. As we continue, the experience of pain is a big part of our sense of touch, or what we also call our cutaneous senses. Pain tells us that the body something has gone wrong, and it usually results from damage to the skin or other tissue or something like that. We can all experience pain for the most part, but there is a rare disease in which a person can feel no pain, and that is known as CIP, or congenital insensitivity to pain, which, if you're thinking like superhero status, that sounds awesome, right? You can't feel pain, you could do whatever you want. But if you can't feel pain, that means you have no idea if some part of your body is damaged or something's going wrong. So those main features of CIP is a lack of pain sensation, which is going to lead to a lot of injuries to your arms, legs, your mouth, an inability to sweat because your body's not detecting that it's overheating. You get infections in your joints, bone fractures, none of which you'll notice unless you physically see it. So think about those times where something as simple as biting your tongue or your cheek while you're eating and how much that hurts. You'd have no idea if you do something as simple as that. Or if you fell down when you're a kid running, you break your arm, you just get hot back up and you have no idea that it's broken and you continue on like that. And things like that can lead to infection. And a lot of times people with CIP, they die early because of these issues, that they don't feel pain in areas that they need to. They can't tell that their body is telling them something's wrong. This girl, Ashlyn Blocker, she's an example of someone with CIP. She feels neither pain nor extreme hot or cold. Those receptors aren't working the way they're supposed to. So she could go outside in the middle of winter, walk through the snow with bare feet, be out there for hours and not notice that she's probably gotten frostbite or something like that. She should be in severe pain, but she's not. So that's one exception to pain, which is something that we all encounter. Everyone's experience of pain, however, is different. And there's a biopsychosocial explanation for this, which we know the biopsychosocial perspective of psychology is kind of the most accepted school of psych in today's world because it encompasses a lot of the most important pieces. So biological influences of pain, it all starts with the activity in our spinal cord, our large and small nerve fibers and the way they transmit and send pain to and from the spinal cord and to and from our brain. There are genetic differences in how people produce endorphins, and the brain's interpretation of that central nervous system activity can be different for certain people. And that leads us into psychological influences, right? The amount of attention you pay to pain can make it worse or can lessen it. Learning based on experience, your experience with pain in the past, and your expectation of pain relief. If you know potentially you have taken some type of medicine that's going to help relieve pain, that might help it go away faster. If you think about you just hit your elbow on the table and all you do is think about how much it hurts, it's going to make that pain worse. If you see an injury and you expect it to be painful, that can make your experience of pain even worse. So psychological factors play a large role in pain, and even bigger than many people originally thought. There's also the sociocultural part of the social aspect of biopsychosocial. This can affect our experience of pain through the presence of others. You might be able to walk it off if there's other people around and you're trying to not feel embarrassed. You can feel pain through empathy for others' pain, and just generally cultural expectations. If you think about the expectations for men and women and how they are supposed to experience pain and who's supposed to feel pain and things like that, there are all sorts of cultural expectations around that. So biology, psychology, and socio-cultural influences, all of those things impact your own personal experience of pain. In addition to that, there's a theory of pain that has kind of become the leading theory on how we actually experience pain, and it's something called the gate control theory. Psychologists Melzack and Wall propose that our spinal cord contains like these neurological gates that can swing open to allow pain sensations to go to the brain, or close and block those pain sensations. What's involved in opening and closing that gate in our spinal cord, they believe, is something called substance P, which is actually the name of the neurotransmitter, substance P. It's involved in transmission of pain messages and tells the gate to open and send the message to the brain, or close and prevent that message of pain being sent. So the idea behind this gate control theory, their research was, they found that when you're in pain, like we said, you hit your elbow, right? And that pain is localized here, right, in your elbow. And there's these small nerve fibers that send that information back to your spinal cord and up to your brain saying like, hey, that hurt, we have pain here, potential damage. But if you've ever done that or hit your funny bone or something, or stubbed your toe or something like that, a lot of our initial responses is to do that and you immediately start rubbing that whole area, right? And what they found was, as you rub that whole area, it actually does help lessen the pain. And there's a couple explanations potentially for that. But they believe it's because when you hit your elbow, those small nerve fibers start to send the message of pain. But once you start rubbing that area, you're beginning to activate the larger nerve endings of your cutaneous or of your touch sense. All this pressure that I'm putting on my elbow by rubbing it is closing the gate to the small nerve fibers of pain and opening the gate for the large nerve fibers that are being stimulated. So essentially my rubbing is a stimulus that's overtaking the pain, and I'm no longer feeling the pain anymore. They've also found that part of that is, a psychological factor as well. Rubbing it, we think it's going to help, so it does. Part of like the rub some dirt on it approach, or the walk it off kind of approach of things when you get hurt. A lot of times that psychological aspect can help. And the way that you put different pressures on your skin can also cause the nerve signals to no longer be sent to your brain. So that's the gate control theory. There's this opening and closing that happens based on the nerve fibers that are being stimulated. As we continue here, what are the main pain messages? Where are they being sent in the brain? So you have your pain sensory input, which if the gate is open, it's going to be relayed by the thalamus, right? All of our sensory information goes to the thalamus first, and then it's directed to the correct place. So after it hits the thalamus, and the thalamus realizes, oh, that's a pain signal, it can go to the somatosensory cortex, where it can judge the pain's quality, its location, and its intensity. How much does this hurt, and where does it hurt? And then it can also go to areas of the limbic system. Remember, this is like our amygdala and hippocampus and things like that. But our amygdala may be part of the reason or part of the way that we respond and help our desire to escape, right? That amygdala can help trigger fear or aggression in a situation where you're experiencing pain and you need to get out of it. And that can also trigger your sympathetic nervous system to get out of that situation. Once it's hit either the somatosensory cortex, the limbic system, or both, it goes to the prefrontal cortex. And after experiencing pain, this is like our secondary emotional and motivational components of pain, where we think about suffering, we worry about the future, how is this going to impact me? And this is much more psychological. And it can, that's where our outlook on pain comes into play. The more you think about it and you have that like poor me thoughts, it can make pain worse, and it can lead to suffering. So that's an experience of pain from the perspective of where it goes and what happens in the brain. Pain control. So we mentioned everyone's experience of pain is different. We talked about the gate control theory. And through that, pain can be controlled by a number of different therapies. Medicine, drugs, right? Surgery to alleviate certain issues that may be occurring, but also things like acupuncture because of placing pressure and stimulation in different areas of your body that can alleviate those pain signals and block those pain signals. Exercise is a great way, just keeping your body in shape. Hypnosis can allow people to overcome their thoughts of pain and things like that. Massage is another great way. They found that when women are going through birth, that massage helps alleviate some of the pain they experience while giving birth. And even thought distraction, changing that psychological part of the experience of pain, you can relieve some of the pain through the way you think about it. Now, there is an interesting topic called phantom limb pain. And in this situation, we know that pain is not merely the result of stimulation. It's not merely physical because of these examples. Phantom limb pain is people who are missing a limb. You can think of soldiers who are, have amputees from an injury, or, a diabetic who's had to have their foot amputated, or for some reason someone's lost a limb. But those people still feel painful sensations that seem to be originating from the missing piece, right? If I didn't have my left arm and it was amputated and I, for some reason, was still feeling pain as if that was still there. And they think this could be due to the fact that there's some cross wiring in your somatosensory cortex, in which once that limb is gone, nearby areas of the brain, or that same area of the brain that was in control of it, it doesn't realize that limb is gone, or they've taken over for the missing limb. So there's still stimulation happening in your brain that's causing a sensation in the missing limb, and it's causing pain. So we know that it doesn't have to just do with the physical sensation or the physical stimulation of something happening to you. Pain is also a very brain-centered psychological thing as well. So our next sense is taste, or gustation. That's what it's also called. So taste and smell are our next two. They're chemical senses. They're known as chemical senses because, unlike the other senses like touch, sight, and hearing, chemicals are actually entering your body, right? When you taste, some type of chemical reaction is happening on your tongue, and when you smell, it's happening within your nose. To taste, we have things called papillae, which are these little dots on someone's tongue. They have the taste buds on the sides of them, on the lateral borders, right? And they connect to sensory nerve fibers, right? Just like neurons, right? That are going to send the message of the taste that we're experiencing. These taste buds regenerate approximately every 2 weeks. And down here, you can see an example of different levels of tasters. People have differing amounts of taste buds in their mouths. A non-taster is someone who has very few taste buds or papillae on their tongue. A normal taster has about 10,000 of these on their tongue, and a super taster, someone who experiences taste very intensely, has upwards of 60,000 on their tongue. So depending on, if you like really, really spicy food, you might be a normal or non-taster because you can handle it. Someone who's a super taster generally doesn't like things that are very flavorful because it's too intense for them. As we talk about the different aspects of taste, traditionally, taste has consisted of 4 specific tastes on your tongue and around your mouth. There are taste buds all over. We have sweet, sour, salty, and bitter. With recent research, we've also found that there is a 5th taste known as umami, which you can think of as savory, like when you have that steak and that flavor is just like melt in your mouth, kind of like delicious. That's umami. There's also something known as astringent, which is more of like a metallic, bittery kind of taste. Now, onto smell, or what's known as olfaction. Like taste, smell is a chemical sense. Odorants enter our nasal cavity to stimulate roughly 5 million receptors to sense and smell. More recent research has shown us that humans can detect about 1 trillion different odors. That is a huge jump from what they thought in the past, and it shows that our sense of smell is much more detailed than we thought, but we just don't pay attention to it as much. But there are about 1 trillion different odors that humans can sense. These olfactory receptors are in the nasal cavity, and this your nose go up to these sensors, which is something called the olfactory bulb, and they can regenerate about once a month. And again, once it hits the bulb here, it continues down. That chemical reaction, chemical information comes in and stimulates your olfactory sensory neurons so it can be taken to the brain. One thing that's interesting about olfaction, or our smell sense, is our brain region, which is responsible for smell, is closely connected with the limbic system, which is involved with memory, aggression, fear. And that is why there are strong memories that are made through our sense of smell. So you can see here, the olfactory bulb actually sends information directly to your amygdala and hippocampal connection, right? It's essentially part of the limbic system. And that's why when you think of you smell certain things, it triggers memory, right? Think about that right now. There has to be a certain smell that when you walk in, you're like, this reminds me of grandma's house. Or you smell a certain cologne and you think of, your grandpa or your parents or something like that. Smell is closely linked to memory as well as reactions of fear and aggression, the limbic system. Okay, a couple other things to talk about. Our senses, that wraps up our 5 senses, right? Our senses interact to produce certain experiences. So that's called sensory interaction. When one sense affects another, that's what takes place. Example here, the taste of a strawberry interacts with its smell and its texture on your tongue to produce flavor. So flavor is not our sense of taste. Flavor is a sensory interaction that's occurring. And that's why they actually tell kids, like, here, if you don't like something, plug your nose, because it's not going to have as much flavor, because smell is a part of that. If you change the texture of a food, it can completely change your perspective of it, your perception of it, right? If you really enjoy, like we said earlier, like a steak, but if you blend that steak up and you change the consistency and the texture, that could make people gag, right? So just by changing these things, your senses interact to produce, certain experiences. And we're going to do some activities in class with our Perception Olympics to practice that sensory interaction that occurs. Our last thing is our sense of body position and movement. There's a couple important terms here. The sense of our individual body parts' position and movement in space. That's called kinesthesis. Are you aware of where your body parts are while you're moving, while you're performing a task? A great example of this, people who have great kinesthesis, high jumpers. They are always aware of their body position, and the way that they manipulate it over the bar is super impressive. Okay? Other people with great kinesthesis, dancers, generally professional athletes, people who have to move their body in complex ways and do it precisely. They have great kinesthesis or body awareness. Our other sense of body position, something we talked about with hearing, is the vestibular sense. That monitors the head and in a way the whole body's position. And this is located in our ear. Those semicircular canals we talked about that are filled with fluid, when those are disrupted, think about when you were young and you used to spin in circles and lay down and stare at the sky and the sky would spin. It's because you're disrupting your vestibular sense. Like this poor guy who can't keep his balance, right? Because his vestibular sense is off for some reason. Once you disrupt those semicircular canals and the fluid is flying all around, you'll lose your sense of balance and your sense of your body's position. Okay? And that's what our vestibular sense is responsible for. So that wraps up our senses and all of our sensational parts of this unit that we're going to discuss. As usual, let me know if you have any questions, and we'll see you for our Sensation and Perception Olympics in class.